name is Roy Simpson. I'm a professor of mathematics at Cosumnes River College in Sacramento, California. This is another proof in differential calculus here. This proof is for the limit of products is equal to the product of the limits. This is actually a very advanced proof in Calc 1. And by the way, this theorem is true as long as these limits exist. In other words, as long as we know what the limit as x approaches a of f is, and that the limit as x approaches a of g is also some finite limit. If we know both of those are finite limits, then we know that the limit of the product can be split into the product of the limits, which is kind of a confusing way of saying it, but some people like that language better than what's written here. The prerequisite keys to success, in other words, what we need prior to doing this proof, we need to know what a limit is. We also need to know the precise definition of a limit, and that involves what's called the epsilon delta proof. You have to know how to do an epsilon delta proof. And finally, we'll need to know the triangle law. This is kind of important for this proof. The triangle law basically says the following. If you have a quantity a and b, and you add them together, and you want to take the absolute value of those, it's just telling us the absolute value of a plus the absolute value of b must be greater than or equal to that. You could kind of test this out with any numbers you want, 1 and 2 for example. 1 plus 2 and then take the absolute value is definitely less than or equal to the absolute value of 1 plus the absolute value of 2. Where you become less is if you're doing a subtraction on the inside. 1 minus 2, that's a negative 1, the absolute value of that is 1. But 1 absolute value plus the absolute value of negative 2 is 3. That's definitely bigger. So that's the triangle law. We're going to use that in our proof. Now let's recall very briefly the idea of an epsilon delta proof. The epsilon delta proof for the limit of a function basically says that somebody comes along and they give you some epsilon, some positive epsilon. What that builds is an epsilon neighborhood, actually, a neighborhood around a certain function value. So let's say you have a function that looks sort of like this, okay? And it wasn't my intention actually to talk about the epsilon delta idea as far as rehashing the whole thing, but I think it's still kind of important. So let's say we want to know what's the limit as x approaches a of f of x. Let's say we want to show that that equals L, in fact. So this means that as we approach a on the x-axis, our outputs should approach a value of L vertically. And what somebody does with an epsilon delta proof, essentially you assume that somebody comes along and says, hey, here's some epsilon. So they give you some epsilon neighborhood around this L. So they say here's a little neighborhood around here, L plus or minus. In fact, this is L plus epsilon. This is L minus epsilon. So they build this wall, this region, if you will, around our horizontal line here, y equals L. And their challenge to you is to find a delta neighborhood around A. So they give you epsilon. We want to find, let me write this down, want to find a delta, positive delta, such that when we build a delta neighborhood around A, and in this case I'll make a really small delta neighborhood here because it looks as though I'll need one. So this point right here is A plus a little wiggle, and this point right here is A minus a little wiggle, and that wiggle is delta. Okay. So whenever we plug an input from that interval, we're hoping that it will always lead to an output between L plus epsilon and L minus epsilon. And if you look at this, it kind of looks like it's going to work. Now, of course, I eyeballed this. But if you look at that delta neighborhood, any x that I plug in from a minus delta to a plus delta will end up landing in this region where the outputs are, I'll just shade them here, they're these outputs, and those outputs are between L minus epsilon and L plus epsilon. So it does seem to work in this case. I found a delta. Now if I had chosen a larger delta, So use your imagination here. I'm going to try to use a different color, but I'm kind of out of colors right now. But if I'd used a larger delta, let's say a delta that went out this far. So let's say this is a plus a different delta. I'll call it delta sub 1. And this will be a minus delta sub 1. Then you could see that I could choose an x value from this delta neighborhood that would lead to an output outside the epsilon neighborhood. So this is not a tight enough delta. I'd have to tighten up this delta neighborhood. So the idea of an epsilon delta proof is somebody comes along, gives you an epsilon, and you want to find the smallest such delta, or maybe not the smallest, but a delta sufficient enough so that you can build a delta neighborhood around your a, what your x's are approaching, so that when you plug in a value from that delta neighborhood, it leads to an output between L minus epsilon to L plus epsilon. That's a brief review, albeit I always find it a confusing review, of an epsilon delta proof. Now here's what we want to prove. Here's the claim we want to prove. That the limit as x approaches some number a of f times g is equal to the limit as x approaches a of f times the limit as x approaches a of g, where these limits exist. That's a very important point. So both these limits exist. Well, before I'm going to start, well, maybe as I start the proof, I'll start by saying we're going to let, since we know these limits exist, let L equal the limit as x approaches a of f of x, and m equal the limit as x approaches a of g of x. Mainly because we know these limits exist, so we'll pretend they're equal to some numbers L and M. Now our goal, somebody came along and they basically said, hey, here's an epsilon. I bet you can't show that this limit is equal to the product of the limits of each of the functions given this epsilon. That's what somebody is doing. So what we want to do is we want to find some delta greater than 0 such that when the distance between x and a is less than delta, in other words, when our inputs are in a delta neighborhood. That's what that's saying. When we input an x where its distance from a is within our delta neighborhood, it will automatically imply that the distance between f of x times g of x and L times M is less than epsilon. Now you might say, well, wait a second, I don't see how that adds up to that. Well, remember, our claim is that the limit as x approaches a of f times g is equal to the limit as x approaches a of f times the limit as x approaches a of g. So what I did is I went ahead and moved over that statement, and we've just said, well, we're going to let L equal this limit right here, the first limit, and G equal the second. So we're really just trying to show that the limit as x approaches a of f times g is equal to Lm. So somebody's going to come along, they give us an epsilon, they say, I bet you can't find a delta neighborhood such that when you plug in an x from that delta neighborhood, it lands in some epsilon neighborhood around Lm. So we want to find this delta such that the distance between x and our limit, our horizontal limit, being less than delta will imply that the distance between our interior function here and our limit of our interior function is less than epsilon. And this is going to be somewhat of a challenge. Now, you know from proving things with the epsilon delta proofs that you have to start with what you're given. You're given that epsilon is greater than 0, so we have to start with the fact that we're told the distance between f times g and Lm has to be less than epsilon. So we're going to start by assuming that we have to work with this business right here. Okay? And then hopefully we can magically get down to finding a delta. And the way the proof starts is a little tricky. So let's take that statement there, the absolute value of f of x times g of x minus L times m. Let's start with that. I happen to know that that's equal to, and here we go, this is going to be kind of a strange thing for you to see, but it's equal to f of x times g of x. And what I'm going to do is add in something here. I'm going to say minus L times g of x plus L times g of x. So really I'm not doing anything to the inside of that. Let me just tack on the minus LM here. All I'm doing is saying, isn't that the same if we subtract a picture and add the picture back? This is a trick we do in mathematics very often, so that we can kind of continue a proof. This will help us out with our proof. In fact, it will help us create a triangle law identity. And this will turn into the absolute value of, well, I could pull a g out of both the first two terms, so it's just g of x times the quantity, oops, not L, how about f of x minus L. And in the second two terms, I could pull an L out of, right? And I'm left with g of x minus m. So far, so good. Now we'll have to use the triangle law here. Since we're talking absolute values, triangle law sometimes is taken advantage of. So this is not equal to, I keep doing silly things like that, it's less than or equal to. I'm going to say that this first term, we'll group that up, so the absolute value of g of x times f of x minus L plus, and then we'll group the second term up, absolute value of L times g of x minus capital M. Alright, so all I've done is add and subtracted the term here, grouped, and then use a triangle identity that I introduced in the beginning of this video to split that group. One final thing I do want to do here is I'm going to just say that this is equal to the absolute value of g of x times the absolute value of f of x minus L plus the absolute value of L times the absolute value of g of x minus m. Now here's what I'm going to state right here. Our goal is to say that each of these, notice there's two terms here, so I'll just write two terms. There are two terms there. I want to show that each of those can be made less than epsilon over 2. So I want to make, maybe I'll write this in red right next to it, want to make each, that's not how you spell each, by the way, less than epsilon over 2. If I do that, then if they're less than epsilon over 2, well then you add them up, they're less than epsilon. And so I want to find a delta to make that true. One thing I need to remind you of is when you're doing a proof, you can only work with what you're given. And we were given epsilon is greater than 0. And we're also given the fact that somebody's challenging us that the distance between f and g, this highlighted thing here, the distance between f and g and L and m has to be less than epsilon. They also gave me one other thing actually. They gave me up above that these limits exist, and we just said let them equal L and M. So we're going to use those right now. I'm going to concentrate on that second term there, and I'm going to try to make that term less than epsilon over 2. Okay, I'm going to try to find a delta so that we can make that term less than epsilon over 2, and that'll be part of our proof. And then we'll find another delta to make that first term less than epsilon over 2, and we'll be okay at that point. Now here's where I really need you, actually this entire proof you need to pay attention because there's just a lot of little tricks to it, but this one specifically, since we're given that the limit as x approaches a of g of x exists, that's part of the assumption, we can say that equals m, we've done that already. So if the distance between x and a, this is just because this limit exists, we know the following has to be true. The distance between x and a is less than some delta, and I'm going to just make a junk delta here, delta sub junk, one that we're not going to use, okay? But I just want to use this in my proof so that we kind of build up an idea here. So if the distance between x and a is less than some junky old delta, then we definitely know the distance between the function and its limit is less than some epsilon, which is just, again, some junky epsilon that I'm only writing in here so that we can build up something. Okay, so that means given, by the way, this is given an epsilon subjunc. So somebody came along and they said, here's an epsilon. I can find, in other words, there exists, that's what that symbol means, there exists some delta subjunc that's positive, such that if the distance between x and a is less than that delta, then the distance between my function and limits less than that epsilon. Okay, great. Now, in our situation here, if we hop back, in our proof, we're assuming we're given epsilon. So somebody came along and said, here's an epsilon. Well, I know, because this limit exists, that given any epsilon, I can find a delta that will make the statement true. So let's create an epsilon here based on the epsilon we were given. This might be it might seem kind of weird, but let's suppose that the epsilon we were given is the following. So we were given epsilon over 2. So suppose that somebody came along and they said, oh, you know what, this proof, they're working with epsilon equals 20. So I'm going to make it tighter. I'm going to give them an epsilon equals 10, 20 over 2, right? Well, we're going to tighten it up even more. We're going to make that 1 plus the absolute value of L. That's an absolute value of L here. Okay. And I said we're making it tighter because the fact is 1 plus any positive number is larger than 1, right? So you have 2 times something larger than 1. This is actually going to be greater than epsilon over 2. Okay? It might be epsilon over 2 times 1.1, right? So that's epsilon over 2.2, which is still greater than epsilon over 2. Oh, I'm sorry. Once I said that, I realized that is not correct. It should be less than. Anyway, so we're given some expression that they say, suppose we're given epsilon over the quantity 2 times 1 plus the absolute value of L, which is definitely less than epsilon over 2. Okay, just plug in any number for L that you want, you'll find out you'll get epsilon over some number larger than 2, and that is, as a fraction, is smaller than epsilon over 2 itself. Okay? Well, if that's the case, just by the fact that this limit exists, then there exists some delta. And so I'll say delta sub 1. Some delta sub 1, such that whenever somebody comes along and we plug in an x from our delta neighborhood, this delta neighborhood, it will imply the outputs, the distance between the output and its limit, which is m, is going to be less than epsilon over 2 times 1 plus the absolute value of L, which again, by the way, it just happens to be less than epsilon over 2. Okay? But that's not important right now. It's just important in a moment. Now let's go ahead and multiply both sides of that statement, this statement right here, by 1 plus L. So this implies that 1 plus the absolute value of L, oops, that's an absolute value there, times the absolute value of g of x minus m has to be less than epsilon over 2. So what does this mean? Well, it means the following. It's kind of a cool little result. If you distribute through, in other words, you just take this picture, this one right here, and distribute it to each of these terms, you'll get the following. The absolute value of g of x minus m plus the absolute value of L times the absolute value of g of x minus m has to be less than epsilon over 2. Now, think about it. This is a positive number right here. Let me highlight it real quickly. This business right here is a positive number. So if this statement that we're viewing right now is definitely bigger than the following statement. The absolute value of L times the absolute value of g of x minus m is definitely less than the absolute value of g of x minus m time or plus, sorry, absolute value of L times the absolute value of g of x minus m, which is less than epsilon over 2. Because, look, this term on the left is missing a positive term. So it's like saying you have 3 is less than 3 plus some extra little bit, which is actually always true, right? So the piece I want you to steal away from this is the following. This implies that the leftmost piece, the absolute value of L times the absolute value of g of x minus m, definitely has to be less than the rightmost piece, which is epsilon over 2. That's what I want us to steal away from this. So we've just shown we can find a delta so that the absolute value of L times the distance between g and m is less than epsilon over 2. We can find a delta. That delta happens to be delta over, or delta sub 1. Okay. So this, we found a delta to make that true. And if we go back to our claim here, remember we wanted to find a delta that would make that green bit right there true. We found it. So that little bit depends on delta sub 1. So I'll write depends on delta sub 1. Okay, so we can find a delta sub 1 small enough to make that less than epsilon over 2. Now we're going to find another delta, delta sub 2, so that it also works for this bit right here, absolute value of g of x times the absolute value of f of x minus L. The problem with bounding the first term here, the absolute value of g of x times the absolute value of f of x minus L, is that this little g of x term, we have two functions working here, and so we'll have to do a little extra work to bound that g of x first. Okay? So again, we're going to actually work with g here because I want to bound just g itself. Again, since the limit as x approaches a of g of x is equal to m, for any epsilon we're given, there must exist some delta such that the distance between x and a being less than that delta implies that the distance between g and m is less than that epsilon. And one thing we can definitely assume here, we can assume that epsilon, whatever epsilon we're given, whatever epsilon we actually started with in this entire problem. So way back in this claim here, I can easily assume that that epsilon right there is less than 1. Nobody's going to come in and give me a huge epsilon neighborhood. It would be too easy for me to prove that using the epsilon delta proof. So we can assume that epsilon is less than 1. Okay, so that means that basically assume that somebody came along and just said, I bet you can't find a delta neighborhood where any input from that delta neighborhood leads to an output in a neighborhood around m of m minus 1 to m plus 1. So in other words, we're given that the distance between g of x and m is less than 1, which is an easy assumption again. And what we're saying is, if somebody did hand me that epsilon, there would exist some delta, and we'll call that delta sub 2 in fact, greater than 0, such that the distance between x and a less than that delta sub 2 would imply that the distance between g of x and m would be less than that 1. Okay, so just by the fact that this limit exists, we could say that. Well, what's important here is that we can bound it by 1, because this will help us do the following. We want to actually bound g of x, right? Well, if you think about it, the absolute value of g of x is the same thing as the absolute value of g of x minus m plus m. So I haven't really done anything. But using a triangle inequality, I could break this up into this first group and that second group. In other words, that's less than the absolute value of g of x minus m and absolute value plus the absolute value of m itself, which is equal to, or I'm sorry, not equal to, actually it's less than, so let me write that in, which is less than 1 plus the absolute value of m. And that's a very important point here. So we know that g of x, the absolute value of it, is bounded above by 1 plus the absolute value of m. Let me write that in. So absolute value of g of x is bounded above by 1 plus the absolute value of m. Now I promise we're almost done. If you go back to the original proof, or the original claim here, at the bottom we have that we have this absolute value of g of x times the absolute value of f of x minus L, right? That's what we want to show is less than epsilon over 2. Well, I happen to know that I can find a delta sub 2 that will bound g of x. So that depends on delta sub 2. So it just depends on how small delta sub 2 is, right? So we have two kinds of deltas here, a delta 1 and a delta 2. By the way, if I choose the smallest of these two deltas, then I still have a bound on my g of x, and I still have a bound on my absolute value of L times the absolute value of g of x minus m. Okay, so far, I found a bound for g of x. I just now need to find a bound for f of x minus L. But go back to this proof right here. And if you just look through this and replace everything that says g with f, let me just write that in red, and everything that said m with L, okay, then I can go over here, let's go ahead and go through this. This was g, I am now going to replace that with f, and this was m. We could do this, by the way, because we know the limit as x approaches a of f of x is equal to L, and we know that limit exists, so this is just the direct idea here. Suppose we're given epsilon over 2 plus, or epsilon over 2 times 1 plus, not L, let's do this as m. So we're switching letters up here. Then there exists a delta sub, well, this is not going to be the same exact delta, so we're going to have to introduce a new delta sub 3, such that when the distance between our x and our a is less than delta sub 3, the distance between f and L, let me just erase that, is less than epsilon over 2 times 1 plus m, absolute value. So this was just from our previous proof. I explained how this is all done in the previous proof. I'm just switching the function now, okay? So this implies that 1 plus the absolute value of m, let me go ahead and write that in there, times the absolute value of f of x minus L is less than epsilon over 2. All we need to do is bound this. Well, listen, I happen to know that f of x minus m plus the absolute, actually it's not f of x minus m. This is me distributing here, but actually I don't need to distribute, so let me erase the stuff down below. Just get rid of all this, so I don't need it in here now. So I've just used all my handwriting from earlier just to kind of really compress all this work. Okay. One thing that you should know is that this little bit, 1 plus absolute value of m, we've just shown that 1 plus the absolute value of m is greater than absolute value of g of x. So that's actually an important part of this. So let me go ahead and go back there and just write in right here that this little bit is bigger than the absolute value of g of x. So the absolute value of g of x times the absolute value of f of x minus L definitely is less than 1 plus the absolute value of m, because 1 plus the absolute value of m is greater than absolute value of g of x, times the absolute value of f of x minus L. And all of that is supposed to be less than epsilon over 2. The outer stuff is what we're interested in, that the absolute value of g of x times the absolute value of f of x minus L is now less than epsilon over 2. So we have shown that for a choice of delta sub 3, this is true. By the way, it's only true because of this right here. This is true if you choose delta, choose the minimum basically of delta 2 and delta 3. So this is based on the minimum of delta 2 and delta 3. So if we go back to our original claim here, that even though this first factor on the first term depends on delta 2, the second factor of the first term depends on delta 3. So the first term totally depends on delta 2 and delta 3. The best way to guarantee that you find the smallest delta neighborhood is to let delta be the minimum of those three. So let delta equal the minimum of the set delta 1, delta 2, and delta 3. That actually completes the proof. If you let delta equal the minimum of those, then it's guaranteed that the absolute value of f of x, this little bit right here, absolute value of f of x times g of x minus lm, in other words, the distance between the interior of our limit and the limit itself, is always bounded above by this product, and this product can be made this small by using the minimum of delta 1, 2, and 3. By the way, this is all less than epsilon over 2 plus epsilon over 2, which is equal to epsilon. That is actually how the proof goes. It's kind of a gnarly proof though, right? Very difficult proof to do.